Okay, so ladies and gentlemen, I'd like you to create a new model, and I'd like you to add an agent class to that model that will be called person. The name of the model, good question. The name of the model will be, we'll do this, SEIRS with network statistics. Okay? For those of you eager to move on, I'm going to try to throw some new things in here, as I am wont. And you can just build this. I'm going to, of course, append or post-pend suffix it with details of the session. I try to post all of these to the website. Okay, so here we are. We want to add an agent class, and we want to have those agents arranged at random locations on the screen and connected to agents according to a distance-based network. The connection range for those agents will be 75. Okay? Thank you very much. Okay, so what do I do? You tell me. What do I do? Okay, so add a new agent type, person, and then add a picture. Okay, we're going to, sure, we'll add, with a little bit more imagination this time, we'll go down and add from pictures down here, come on, pictures, we'll add a person using this shape here and put it up there, okay? There we go. Great. We'll see how to do something a little bit more advanced than our circles to which we have been confined. The circums that have circumscribed our visualizations. Okay, so I'd like to create a time unit of days in this model. Where do I go for that? Okay, the whole project and go to days, right? Go to days here. Okay, great. So that tells us if it sees a 1, it knows it's 1 day. If it sees a 2, it's 2 days. If I set it to year, we would interpret a 1 as 1 year. Okay? Good. So far, some good. So, ladies and gentlemen, I'd like to set these individuals so that they can be placed in a network with connections displayed. First of all, how am I going to put them in a distance-based network? You tell me. I want to put them in a population. What do I need to do? Okay, so I need to drag this in. Good, this should all be reviewed for your folks. So here's a population. Remember, agent-based models consist of one or more populations of agents. Here's our population, and I need to indicate, of course, it's a population of agent, and it's going to be size 250. 250 individuals in this population. Okay? Great. Okay, now I want to associate, I want to have that population be associated with a layout that's uniform in the X and Y location. They're equally likely to be placed at any given point in the X and Y location. How do I do that? Okay, main, go to properties, scroll down, and to this area environment for other agents, right? And I can do a what? Is that a function of layout type or network type? Layout type. Layout type has to do with the geometry, where people are placed. Network type has to do with the what? It has to do with the topology, who is connected to whom. Okay? And speaking of topology, we want to have what sort of network type? We want a distance-based with distance 75. What does that distance 75 mean? trying to hit here on office hours themes. What does it mean to have a distance-based connection with a distance threshold of 75? Connection range of 75. Good. So you hit it on the head. If we consider any two pairs of people in the model, those two pairs will be connected if and only if they lie within a distance of 75 distance units of each other. Otherwise, if they lie outside of that, they will not be connected. So ladies and gentlemen, as this rises, in general, are people connected with a larger number or fewer connections? Larger number, right? It's more permissive. It's more relaxed. It will consider them connected even if someone lives a long distance away, perhaps. The smaller it is. If it's 0, they're not connected with anyone except someone put precisely on top of them. And the chance of that is infinitesimally small. So the larger this is, the more connections people have. Great. Okay, ladies and gentlemen, I'm going to ask you this. I'm going to run this model right now. What am I going to see? Scattered agents. Do those agents have connections? Where the connections goest? Where are they? Okay, why don't we see them? Okay, let's illustrate that let's show that they do have connections. Okay, now I'm trying to throw in some spice for those who are for whom this is a little bit routine. I want to set up a histogram that will show the number of connections associated with agents in this model. I want to create a histogram that will depict the number of connections associated with agents. So it's going to give a distribution of sorts, right? Each little area in the histogram, this will be the number with 0 connections, 1, 2, and it's going to count the number who have that certain number of connections. So, it's going to go something like this, and then maybe it go down. Okay? So this is the number this is number of connections, connections K, and this is number of people with K connections. Okay? Connections. There we go. Okay, so how are we going to do that? Where would we look here? Where do we look? This is partly to address those who are doing projects and struggling with questions about where to go to do things. Okay, so we would put it in main because we're dealing with something about the whole population, a histogram across the population. And, okay, we're going to go to palette, we're going to go to the analysis component of it. So, analysis, and then where do we look in the analysis area? Sorry? Histogram. Okay, so let's pull out a histogram. And let's put it up above here. I'm going to put it up above that area, okay? Here's our histogram. Is that all we need, though? We need to actually define the data associated with it. So there's a thing called histogram data here. We're going to drag that up. Okay, so this will be, we're going to call it degree centrality. Histogram. Okay. And actually, I'm going to be a little bit more wordy for reasons that will be coming up. Person degree centrality histogram. For each person, we're going to consider how many neighbors do they have. Okay? Great. A fine thing that is. Okay, we're going to now need to populate it. How are we going to populate it? Right now, does the network change? If there is a network, does it change? Okay, so we can populate it in any number of different places. One way that we could put it is in main, you could put some code in on startup. And that means when main starts, it will execute this code. This is a handler for built-in event when it starts up. But a way to make it a bit more transparent, one of the big challenges of this package and of some other agent-based modeling environments is the fact that code gets scattered around everywhere, and you may not see it. So one way to do it is to drag out an event, which will be like initialization event. Or better yet, think about the software engineering principle of separation of concerns. Let's call it initialize connection histogram, something along those lines. Okay, and this will fire at what point? Well, right now, it will fire a single time, occur once, at time 0. Remember events? They can be set to fire off at specific times or with a certain rate or under a certain condition. And they can live in a person or in main. And this one lives in main. It's going to fire a single time. And what are we going to do with that event? What's the point of it only going off once? Well, when it goes off, we need it to do something. And what do we need it to do? What do we need this event to do? Yeah. Good, good. So it's going to place into this data set, this histogram data set, it's going to put information of a certain sort to be, for which a histogram is going to be made. What's that data going to be? It's going to be the number of connections. Okay, so all those computer scientists who sit arrayed before me speak as in one voice. How would I loop over the population to call each person P in turn? Okay. Pardon me, this experimental app is seeking my response to a bunch of surveys. No. Okay. Pardon me. It is exhibiting a bug. Okay. Okay, so what we need to do is for person P. Where's James? There you go, man. Okay, so person P in population, and so we're calling each person in the population in turn P, and with that person P, what are we going to do? We're going to add their data on their number of connections to person degree centrality histogram. So person degree centrality histogram, boom, dot add. What are we going to add? We're going to add their get connections number. No, I can't. There it is. Boom. Okay. Can you folks see that? Okay. Let me put it up on the big screen. Okay. So let's put it up on here. Hey, come on. Okay. There we go. How is that? Is that better? Okay. So we're just looping over each person in the population. Gosh, some of my software engineering students, I sometimes still see them using like the classic Java iterators from 20 years ago where you called get next or something like that. Ladies and gentlemen, if you're going to iterate over a collection in Java, this is a sweet way to do it. With Java 8, it's sweeter yet. There's some really, really nice ways of filtering and collecting, reducing from, mapping over collections. And we may get a chance to see those late in the course. But this isn't bad. So you're iterating over each person in the population, calling them P in turn. And then for that person P, you're getting the number of connections that they have, and you're adding that to this data set. Okay? People comfortable with that? Any questions about that? Okay? Yes, Richard. Right, right. Get connected agent. Okay, so you're asking about the difference between, say, p dot get connections. Okay, it doesn't know p because I'm outside the scope. Pardon me. While I fool it. So give me a second here. P dot get. You're saying connected. Sorry. Get connected. Come on. Get connected agent. This will get the agent who is your ICE connection, your index connection. So if it's index 0, it's your very first one, index 1, second one. You can also get connections, which gives you a list of all those agents to whom you're connected. But you don't have to frob your code in the way I just did. That was just to answer Richard's good question. Okay, other questions about this? Okay, the light bulb. Oh, okay. This is a very, very, very good point. Good question. Why is there this light bulb over here? Pay attention to light bulbs. Light bulbs typically will give you important information, and very often it's contextual information, variables that are contextually defined at that point. So, for example, self here, if I use the term self, it would refer to the event that's being triggered right now. So I could refer to the event that's in my context. And in general, the light bulb will clue us into variables that are contextually defined. So they're defined to tell us things about our context. Oh, this is just there permanently in case we want to have recourse to asking about this current event. Like if we wanted to disable it from now on, we could refer to it as self. Yeah. Okay, great. Okay, so ladies and gentlemen, let's go run that thing. And up here, we should, hey, oh, what have I not done yet? Yeah, we need to link this up to the data. So we need to do add histogram data, and this will be degree centrality. That means the number of connections that a person has, just the number of connections. We talk about, in social network analysis, we talk about several types of centrality, degree centrality, betweenness centrality, and eigenvector centrality. These are different measures of how well connected or how central someone is to a network. In this case, it's particularly simple. It's how many connections do they have? Betweenness centrality would be on how many shortest paths between other pairs of individuals are they located, for example. So degree centrality, what we want to say here is we want to actually just refer to that person histogram data set. I should have called it data, sorry. I should have called it data. Histogram data, this one here, to avoid confusion, but I'll just leave that name for now. So this chart needs to be wired up to refer to this data. Why? Because we are putting the information into that data set. Does that make sense? Okay, so let's run this thing. And what should we see? Oh, run this thing, we should see an error message. Okay, degree centrality histograms. I said histogram instead of histogram. Sorry. Build early, build often. I could have caught that by doing a build here. And let's run it. And we should see a histogram there. What that's showing, undeniably, is that people are placed in a network. Some people have more connections than others. The mode, the most common number of connections, is somewhere between 15 and 20 on the upper side, maybe 18 or so. And but we have some people with as few as 4 or so connections, and some with up to 30 or so connections, just short of 30. Okay? Okay, so ladies and gentlemen, let's now connect people up visually, though. We have a network. There's a network there. Why aren't we seeing it? Okay, so we have to go to person, and we actually have to go up, and their connections are reified. What do I mean? For those from computer science background, What do I mean by reification? It's actually a term that comes up quite a bit in certain areas of computer science. If we say a programming language has reified the stack, or it's reified the heap, what does it mean? It means we make it tangible in a sense. We give it a name, make it an object so we can refer to it, we can interact with it explicitly. It's not merely in the background. It's not merely hidden from us, merely implicit. It's something we can interact with. And here, connections are treated as they're given sort of full properties and names themselves. So we have to go to these connections, and we can associate actions, behavior with the connections. One of the actions is by setting animation. Incidentally, this idea originated in this very building with our research group, and they adopted it. So we're going to go down here and do draw line connecting agents. And we'll say draw it on top of agents. There's just so it's not hidden behind agents when the agents are particularly dense. So we're going to do draw on top of agents. Okay. So now we should see agents arranged visually in a network, shall we not? And it should match that sort of histogram here. Now, some of you may notice something. Does anyone notice a difference? I just ran it again and I saw this. Did I change the network type or assumptions? Why is it different? It's random. There's stochastic randomness here. We're going to be coming to that in a big way. After we cover the third type of modeling, we're going to be looping around. That's something that applies across multiple modeling types. We're going to be dealing with this randomness. The fact that every time we run a model, the results are different. But for now, we merely remark on that fact. Later, we'll see how to grapple with it and how to develop recommendations that are robust, even given that uncertainty. Okay.
There is connections in main. I did it in the main, but
indeed.
it didn't work.
Okay. So let's talk about that. The connections that we modified to make it visible, where did they live? They lived in person. We're talking about making a person's connections visible. Why does main have connections? Well, in general, every agent has connections. And it would be a little bit strange, admittedly, if main was arranged in a network of mains. But in general, every network has some connection, and those in main will typically just not be used. But they're provided as a routine matter for any agent. So we don't have to differentiate between a special main class versus other classes. We could just treat them all as kind of agent classes. Main is actually an agent.
Can we connect different agents?
Absolutely, yeah.
And in that case, where we should do that?
Connecting agents to each other?
Yeah, different agents. I mean,
different types of agents.
Yeah.
Could you have a person connected with a car that they own or with a dog? Yes, you can. You can. And you could have them defined in the connections for the person. This is exactly the sort of thing I like doing with you folks together rather than having you watch a video. So, for example, we could connect individuals within here to other agent types. We could have individuals connected to their doctor or to their home or something like that. So if we wanted to, we can connect different types of agents. Okay? Very good. Okay, so we now have this network, people within the network. And I'd like to observe, folks, just as a matter of reflection on things. If we change the network type from distance-based to be scale-free, for example, make it a scale-free network, how would we expect to see the histogram differ? What do we expect to see for a scale-free network? So I'm just going to temporarily make it scale-free. What do you think I'd see when I run this thing for the histogram of connections? Yeah, it's going to be dropping very sharply. Remember this? It drops off very quickly. Most have very few, some have a lot. Suppose I were to make it instead a type of network that is has a ring lattice network. What would it look like there? Well, everyone is the same number of connections, right? They're all right around 2, and in fact, it's exactly 2. That's going to have a very material impact on the number of connections that people have. And you could experiment more with that, and I'd encourage you to do that. So what would a random network look like, do you think? On average, people say have 2 connections. I could make it a larger number. But do you think there'd be any variability? Maybe I'll say on average 5. Do you think there'd be variability? Remember, every pair of people has a certain chance of being connected. You bet there's variability. It's not that wide compared to others, but there is variability about the average. Okay? You should be aware of this. A little bit of learning. Kind of we're doing not quite a grand tour, but we're reflecting on agent-based models and their characteristics and some of the things such as networks that accompany them. Okay, so ladies and gentlemen, let's switch this back to a distance-based network. Great. Where'd my mouse go? There it is. Distance-based network, there we go. Okay, so ladies and gentlemen, now I'd like to go and I'd like to add a state chart. I would like to add a state chart where we have individuals in a type of progression where they start susceptible. They go to an exposed state where they're infected but not yet infective. They go to an infectious state where they remain for some period of time. And then they become recovered. Okay? I was thinking that we'd allow them to get susceptible again, and we may eventually do that, but let's see how time goes. Okay, so let's go to person. How are we going to add such a state chart? Sorry? Okay, the palette state chart, okay. And we're going to add them in. I'm going to throw in another twist. This will be really good for reinforcing some things. We're going to have them, when they're in the infectious state, they're going to have a chance of dying as well. About a 50% chance of dying and being removed from the population. And the chance, and we'll get some extra understanding of one of the reasons I'm proposing that in a little bit. So this is going to be state infection state chart, we'll call it. Okay. If we just call it, ladies and gentlemen, naming is important. Those who are going to take software engineering from me will know that I feel very strongly about this. If you call this infection, it might be fine, you look at it and it just says infection. But when you go do autocomplete, you do person dot and it says infection, you don't know if it's the name of a state, you don't know if it's the name of the whole state chart, you don't know what it is, infection. So it's good to give names to things to remind you of what they are, what function they play, the sort of thing that they are, so you have a sense what you can do with them. So infection state chart. Okay, so we're going to add a susceptible state. We're going to add an exposed state. We're going to add a infectious state. And we're going to add a recovered state. You notice I'm adding them some distance apart. Why? Nope, recovered. This is what is recovered? A past participle, I think. Generally we use verbs like recovery. That's not a verb. Now I'm describing a process for the transitions. But why am I putting them so far apart? Yeah, and lots of transitions to be shown more clearly, like what type they are, and also to show their name clearly. So we're going to have a link from susceptible to exposed, representing that progression. Similarly, a link, and maybe I'll copy it here, and then I'll paste it down here. Another link from exposed to infectious. and another link from recovered, infectious to recovered. Okay? There we go. Okay, ladies and gentlemen. This is going to be a contagious disease. With what sort of link would that from susceptible to exposed represent? Exposed here represents someone who's infected, but not yet infective. It's during the incubation period. The latent period. Actually, it's not only symptoms not appeared in this case, but you haven't become infectious. So with what sort of transition would that be associated? What are the types of transitions? Who can speak to that? Give me some types of transitions. Okay, rate, timeout. What does a timeout transition mean? If I have a transition that's a timeout of 10, what does that mean? Oh. Okay, so if I had a transition out from susceptible to exposed to timeout of 10, that would mean exactly 10 time units after they come into susceptible. If they haven't left by any other transition, they're going to be leaving by this transition. That's what a timeout means. Do you always have to specify a timeout with a fixed number? No, you could give an expression, and all it means is when they come in here, it will evaluate the expression. Maybe it's a draw from a random number distribution, draw from a uniform distribution between 10 and 20, and it will draw a number, and then that amount of time later, it will go off, and they'll leave. Question about that? Timeout? Okay. Yeah.
Timeout assumes then 100% of the population votes?
Well, remember, this is just describing a single person. This is the state chart, it's a very, very important point. In a way, visually, this is very similar to a stock and flow model. But remember that this represents for a single person. And so, if all of the population were in the susceptible state, and they came into it at the same time, yes, they'd all leave at that same time. But some may come into it at different times, some may be in different states. That transition, ladies and gentlemen, only applies to those in the state from whence it emerges, from whence it comes. Right? Okay. So this is susceptible to exposed. So one type is timeout. Another type is rate. What is a rate? What would a rate of 0.1 mean? Okay.
There's a 10% chance per time unit.
Yes, yes. And this is very similar to the situation where we had a stock and we would have a flow out of the stock that associated with some alpha, maybe equal, say, 0.1, and you have a certain, each person in the stock, some group of people, P, they'd have a certain chance per unit time of 0.1, maybe it's 10% chance per year of developing diabetes or what have you. Now, the formula here, let's call the stock X. The formula here will be alpha X, right? The idea here is very similar. If this were a rate transition with a rate of 0.1, it'd be very similar, but we don't have X because it's applying to a single individual. It's the chance that they will move from that state to that state for them. So it's equivalent to the alpha, the chance per unit time of going from one to the other. Does that make sense? Okay. But a very similar issue in a similar mathematics. Ladies and gentlemen, riddle me this. If we had 1,000 people in this stock originally, and it's a chance per unit time of 0.1, they come out. What is the number of people in the stock? How does it decline over time? This is a stock and a stock and flow. How does it decline over time? It's exponentially decreasing. It's e to the minus alpha t. Remember that? So it'll be going something like 1,000 up here and be going going down and down and down. So it is, ladies and gentlemen, with the probability that someone remains in the susceptible state after time t at an individual level. They'll be going down in a similar way if they're not removed by any other transition. Okay, so those are two types, timeout and rate. Both can change over time in the sense that we could recompute the rate or recompute the timeout periodically, but while it applies, you'll leave in a fixed amount of time later if you haven't gone through others. Okay, there's other types too. Condition. Arrival of an agent. But in this case, ladies and gentlemen, what are we going to use? Riddle me this. A message transition. Good. This will be a message transition. Okay, so, and this will be called infection. Okay? Good. Ladies and gentlemen, infection. Okay? Now, the exposed to infectious, by contrast, will be associated with a timeout. This will be called becoming infectious, let's say, or becoming infective, be associated with a timeout of 21 days. Does anyone know an infection that has a 21-day timeout? 21-day time of incubation? Ebola. Okay. And then from infectious to recovered, we're going to give it a mean time. This will be recovery of this will be a timeout, let's say, of 14 days before they lose infectivity. Okay? Except some of these people are going to die in the infectious state, while in the infectious state. How would we capture that fact? I'm sorry?
Another step,
a
branch.
Okay. A branch is tempting, but we actually don't need it in this case. What we could do is we could put this final state in. That will represent death. And then we could have a transition from infectious to there. Okay. Now, just to ease the mathematics of it, what I'm going to do is to say that this transition to death is going to occur with a rate transition. So this would be dying, and it'll be with a rate transition where the rate is 1.0 divided by the amount of time it takes for them to go from infectious to recovered, 14. However, as a software engineer, this gives me the willies. Stronger than that, it gives me the heebie-jeebies. It's really unpleasant to see these 14 scattered in. How do I know one 14 is logically the same as the other? If I go to change one, I might forget to change the other. What we should really be creating here is what? A parameter. Okay? And what we will do is we'll associate with a parameter called mean infectious period, or mean time to recovery. That's better, mean time to recovery. And we're going to make it 14 days. Okay, it'll be a double, 14 days. That will allow us to change it, among other things. Giving it a name allows us to change it, to reuse this model with different assumptions about it. And most importantly, it makes it more transparent about where these numbers come from. And so now if I have infectious to recovery, this will be based on mean time to recovery. And this transition here, dying, it'll be associated with a rate was 1 over mean time to recovery. So here's a question, folks. What fraction of people on average will die here before recovery? Reason about it. They have a chance per unit time of 1 divided by mean time to recover to go from infectious to recovered, and they'll go from infectious to recovered to mean time to recovery time. What fraction will go each way, roughly? 50%. So about half of people will die, half of people will not. Okay? Okay. Good.
I have a question.
Yes.
Did you put a transition from each of those states to the death state?
Yes, you could. Yes, you could. In fact, more than that, if you had multiple state charts, they could all have a transition to the death state. Yeah. Okay. So, ladies and gentlemen, we're approaching a pretty nice little model here. But there's a few things we want to do. First of all, how do we make these people, when they die, we want them to disappear from the population so they don't infect others and not counted in the number of live people, etc. So how do we do that? How would we do it so when they say enter this state, they're removed from the population? Well, who maintains the population? Maine. So what we actually have to do, and this is an important lesson, if we want to refer to something in Maine from person, I think you've seen this in a video, but just want to reinforce it. You can actually refer to Maine. Where does this Maine get magically defined? Well, you'll notice up at the top here, this thing called Maine, which points to its context. Or you could say this .get Maine if you wanted to, but you could just say main dot population dot remove. Hey, oh man, sorry. Main dot remove population and give it this. Okay, that may be new. That's interesting. Whereas delete self, remove this agent. Oh yeah. Oh, okay, that is nice. Okay, so that's even cleaner, isn't it? Because then we don't have to say which population. So very nice. Thank you very much. That's great. Delete, that seems to be a new innovation. Delete self. We can just say that's our action at this point. Delete myself. That's cleaner. We're not coupled. Why is it cleaner? Because we're not coupled to the internal representation of Maine. This is a software engineering issue. Ladies and gentlemen, if we have a system that's composed out of multiple parts, it's very important that we have a separation of concerns to avoid it becoming a big hairball where you change any one piece and the other parts break. The pieces should not depend on all the vagaries, all the details, all the how of they're each implemented. They should depend only on broad what the other thing implements and not on the how. And that's what allows the flexibility to change the internals without breaking other things. So in general, when we build systems, we don't want to couple the pieces together. We want them to be fairly independent. When we had that expression here, we went up and referred to the internals of Maine. It depended on whether it was remove population or remove pop, depending on the vagaries of what the population was called. This is cleaner. It doesn't depend on the internal representation of Maine. It's an important principle, abstraction. And we achieve it, for the most part, by working through interfaces. But this is an example where we can decouple the situation nicely. Okay? So this self. So people can leave via that. Okay, ladies and gentlemen, if we ran the model right now, what would we see? Yes?
I just have one question. I'm really sorry. What's the transition from that book to close?
Sure. No problem at all. I understand, odd things come up in the course of building it and you miss a step. So welcome those sort of questions. It's a message transition that's unconditional. Okay? Okay. Ladies and gentlemen, what would happen if we ran the model right now? Okay, nothing. Why not? Okay, there's no initial infective. That's right. Okay, so that's one element of it. Let's suppose when we went to try to, we wanted to have it so when we click on a person's picture, then we infect them. How do we do that? So what we did is we went up and went to this here, and we can go down to the advanced area and set it so in the on-click area, we could say, for example, this dot send infected exclamation point, comma, and to whom is it being sent? This. What is this? It's referring to me. For those not from computer science background, this, that, this. Okay, the word this denotes a reference to the current object. So it's saying send myself a message, send myself a message. I send myself this message infected when I get clicked. Okay? Okay? Well, they're exposed and then they'll become infected eventually. They are becoming infected. They're not becoming infective yet. They are going to become exposed, where they're infected. They're just not yet infective. Does that make sense? They go into that exposed state, right? The receipt of that message by someone who's susceptible will bring them to the exposed state. Okay? Okay, ladies and gentlemen, how could we make it so that it's visually obvious? Change their color. How can we do that? Yeah. Now, as a software engineer, I have a little bit of torn feelings about this issue. One thing the simplest thing to do here in front of you, in the sense that it's accessible to everyone, is to create a color variable and to call it of type color. But I have some reservations about that, truth is. A part of me wants to create a function that says get color, and that could take all sorts of things into account and could just return the appropriate color based on their state, based on other characteristics, without having to litter our model with lots of assignments to this variable. But we'll do it this way. So coming into the susceptible state, color will be set to green. Coming into the exposed state, color will be set to orange. Coming into the infectious state, in the entry action for that, color will be set to red. And coming into the recovered state, color will be set to gray. Okay? There we go. What do we still have to do to make that actionable? So in other words, I did green for susceptible. For exposed, I did orange. For infectious, I did red. For recovered, gray. Okay? What do I still need to do to make that actionable, to actually make it their color visually? Click people. Okay. Now, this is where we're going to run into a little bit of turbulence. So we got to person, and you'll find this is why I was using those nice circles, those stylized circles. For physicists will talk about spherical cows, and there's a certain utility to them. That's why. I don't mean, well, yeah, to that conception of a cow. But if you click here, there's actually, in person, there's no color given. Oh, so there is, right here. Okay, I just changed there. If I go here, there's no color. But if I go further consider its constituent parts, if I go over to person, go to presentation, and go to shape body within it, over here on the left-hand side, that's when we can get to fill color. These are the sort of things I don't have time to talk about in most lectures, but you get by having a bit of a retrospective like this. So I can call this color. How did I do that? I clicked on this thing here. I went over on the left-hand side to person, and I drilled down under presentation to where it said person, and then I created shape body. I selected that, and there I could set the fill color to be color. Okay? Okay. So this is their body shape, and we're going to make it according to color. Okay, so that's great. Now you notice it's still complaining about something. It's still complaining by virtue. You could see these red X's. Let's go see where we can deal with that. How do we know what it's complaining about? What it's complaining? We can go to View menu, Problems, and you'll notice it's saying that this thing is not reachable. Can anyone see the problem here? Yeah. Yeah, exactly. So I did View, Problems. The Problems window is your friend, ladies and gentlemen. Friends are people that sometimes tell you your problems so that you can improve them. Sometimes it's a bitter truth to swallow, but it provides that opportunity to learn and to change in a favorable direction. Here, this falls short of it, and so we need to drag that over. We need to drag it over there so it turns green. And thereupon it turns green. So now if we go to View, Problems window, it stands blank before us, and we are ready to simulate. Okay? Are people comfortable? Are you following along? Sorry? You don't need to put any message. You could just say, it's a good question, Sogat, and what you could just say, do it unconditionally. That would mean whatever message is received, we're going to transition. I'm showing two different ways, incidentally, of starting that initial infective, from the one you did in your problem set versus this one. So here we could click on someone, and you'll notice if we click on them, they will get exposed, and then in the fullness of time, they will become infected, and some of them will die. Right? Okay, ladies and gentlemen, why isn't the infection spreading? No, we're not sending messages when we're sick. So, ladies and gentlemen, where would they send messages? In what state? Infectious state. So we'll go down and we'll add a transit. How do we have them send messages while in the infectious state? There's several ways we could do it. We could add an event which only fires in that state, but the easiest way is with one of these arrows. And let me just make the point, folks. I'm going to do an internal arrow, which means they don't leave this state ever. They don't leave this state while this fires. It just fires periodically. By contrast, if I did one that went, if I did one which went outside of this, like this, oh gosh, it's degenerate. If it went outside of this, kind of like this, it would actually leave the state but come immediately back into it. So I'm just going to have it stay within the state, and what's going to happen is that some number of contacts per day, let's go set contacts per day with a parameter, contacts per day, okay? We're going to, here in this transition, this will be called transmission. We're going to have a rate that will be contacts per day. Now, that's something we have to be kind of careful. This is potentially infecting contacts per day, because if someone gets that message, who's susceptible, they're going to get infected. Okay, so it's potentially infecting. That should really be what it's called. We're actually not measuring all contacts. We're measuring the number of contacts that could actually transmit the infection. potentially infecting contacts per day. I have an extra I in there somewhere. There we are. Boom. And then this is going to be going at potentially infecting contacts per day. What that means is, if we consider all contacts, you know, they brush up against someone in the market, they comb their daughter's hair, what have you. Be a huge number of contacts potentially, but these are contacts which might spread fluid, for example, from an Ebola patient. Okay? So this potentially infecting contacts per day, we're going to assume that the value here is one contact per day. Okay? Okay. Ladies and gentlemen, what's going to happen at that contact? We still haven't finished that transition. This is not all. What do we still have to fill in? Sorry? The action. And what's that actually going to do? Send a message. This, I am going to send a message, send to random connected, one of my connections in the network, a message infected. Now, ladies and gentlemen, what will happen if the person who gets that message is in the susceptible state? They'll transfer to the exposed state. What will happen if that person who gets the message is in the recovered state? Nothing. There's no transition from that state, which depends on that message. Does that make sense? That's a very important point. If that message is received by someone who's not in a state that can get a message, it'll land on stony ground. It won't go anywhere. It won't make a difference. It will disappear as if it's a stone dropped into the ocean. By contrast, if it's received by someone who's in a state like susceptible, where there's a transition out that's a message transition, it'll make an impact. Okay? Are people comfortable with that? Okay, ladies and gentlemen, can we run this thing? What did I make potentially infecting contacts per day? I made it 1. And again, for those who want to see it, I'll go put this up on the big screen. This is what I put into the action associated with the transmission of infection, this periodic transmission of infection. Okay? So that periodic transmission of infection is a rate transition, and it's potentially infecting contacts per day. 3 per day, 1 per day, 0.5 per day. Okay. Can we run this model? Okay. Let's run it. Okay. So we're going to start with this index case here. Why isn't anyone getting infected? I just clicked in. What? Yeah, it's not 21 days yet. Okay. So now they've turned. Okay. Now what's starting to happen? Okay, it's spreading infection. How many people would be reported as infected? 0 now. But what's going on? Okay, now it's another whole generation, right? But you notice what's happening now. Also, there's connections being broken, right? As individuals, what? Die. The network is being affected from that. Okay, so ladies and gentlemen, we want to analyze this now. Are you folks seeing that? No? Okay, so what are you seeing? Okay, so do you have a time to go from from exposed, from infected to recovered of mean time to recovery of 14 days? 14? Yeah. And within the infectious state, it should be a rate of 1 per day. It sends a message to a neighbor. So in debugging these models takes care. So one thing I would do is ask, is the person who's infected, do they go through, do they die prematurely? Do they disappear often? Or do they go on, become infective, red, and then turn gray? And if the latter, then I would investigate whether they're spreading the infection, and let's say whether they're transmitting it to others. And if they're dying prematurely, I would check the rate at which they're dying. Okay, so this will take a little bit of sleuthing. Okay, ladies and gentlemen, I would like to add now some statistics. So I would like to add a statistic for the number of infectious people right now. This is a cross-sectional statistic.
Okay.
Yes?
Does that message itself have any meaning? I mean, infectious.
No.
Instead of infectious, we write, for example, be happy. Makes any difference? Or?
Right. If it said, if you had the message "be happy," would it make a difference? No. Why doesn't it make a difference? It's an unconditional. The only one place in this entire model depends on that message. Which place is that? It's this from here to here, and that depends on unconditional. Just the very existence of the message transitions them.
If we had two types of messages in this case.
Yes. Then you could check, is the message equal to one or is it equal to the other? Okay? The robust way to do it is to make them optionless. Okay? Okay. So, ladies and gentlemen, incidentally, I'd be happy to help debug that model after class if there's a need to, if you want to bring it up. Okay, so what we're going to add now is some statistics. I want to add a statistic to count the number of infected people right now. Where would I go?
Main population.
Main to the population here, and we want to do add statistics, and this is going to be count infective. Okay? And you'll notice we say we count the number that match some condition. What's the condition going to be based on? On what is the condition going to be based? Their state. Yeah. Their state with respect to what state chart? Infection state chart. So the condition is going to be this dot, excuse me. Whew. Okay. You'll notice that once again there's a light bulb. The light bulb is our friend. It gives contextual hints. And what it's telling us is that there's a variable called item, which refers to each person in the population in turn. What population? Because this is a statistic in the population. Item, it's going to go through each item in the population. In this case, it's a person. Calling that person item in turn. And it's going to run this condition, this criteria. And it's going to say, do they meet the criteria? If so, we'll count them. Otherwise, not. So the condition here is some test. It's going to return true or false about whether they meet the criteria. So here we want it to be item dot infection state chart. We're going to ask this person's infection state chart, is state active? And which state? Well, it's the infection person dot infectious. That's the state. It's infectiousness with respect to person. We could have a model with deer, with people, with dogs, and we want to distinguish infectiousness with respect to a dog, with respect to a deer, and with respect to a person. In this case, it's infectiousness with respect to a person. So it's person.infectious. For those from computer science background, what sort of variable is this? It's a static variable. It's a static constant. Static integer, short integer constant, for those seeking to know. So, each person in turn in the population will be called item. We're going to ask for that person, their infectious state chart, hey, is this certain state active? Right? Okay? Each such person will be indicated. So, ladies and gentlemen, I want to create a chart of this now. How do I do that? Riddle me this. I want to create a time plot. Where do I go? Analysis, go to time plot, pull this up, and I want to plot out in the time plot. This is going to be plot infectious cases, and I'm going to add a data item, and I'm going to call it infectious cases. And how do I compute that statistic? So now I want to use that statistic. What do I say? Yeah, this dot population, or just population, if you will, dot count infective. You notice it's a function, it's a method, folks. When we define that statistic, it becomes a method. AnyLogic defines that method. You can do Control J in the code for the statistic. You'll see the method that AnyLogic creates for it. Just a loop through the population to count. Count infective. Yes, Richard. Yes. Okay. I'm going to put on my language engineer hat. In computer languages, we distinguish between two types of things. One thing is a statement, which is like a command. Do this. Change this. It typically involves modifying, it involves side effects. It involves modifying something, the memory, sending out some information over the network, changing an appearance on the screen, whatever. That's a statement. It's a command to do something, perform some action. The other, by contrast, we have things called expressions, which are formulas, right? They compute a value. We need semicolons when we have statements. We do not need semicolons. In fact, we don't have them. We don't want them when we have an expression. This is an expression. It computes a value, and so we don't need a semicolon. If it were a statement to do something, an action, that, like, for example, that we see here, then we need a semicolon. Does that make sense? Yeah. So, in short, if it's computing a value, if the end thing is that you get a value, you probably don't need a semicolon for it. Okay? So, ladies and gentlemen, here would be the number of infectious cases. I'm going to infect someone here. No infectious cases right now. Why not? Yeah, okay. So, is the infection gone now? No. You notice it's kind of going through generations. You see that? It's almost like multiple generations. A first generation. Wow. You're the man. Thanks a lot, James. Much appreciated. You notice it's almost going through these multiple generations. Even now, you can kind of see the oscillations. Do you see that? What's going on there, folks? Well, with such a big time where it's, people are not yet infected, you can have very few susceptibles at first. There's kind of a wave of infection. People get infected. But the next generation of infections has to wait for what? For those people to become infective, to become infectious. And that's when that new wave generation can take place. So if you were to change the incubation period from 21 days to 50 days, you'd even see it more pronounced. You'd see those kind of waves, those multiple generations of infections even more clearly delineated here in terms of they come and go, they wax and wane. Here we go. People are infected, but not yet, it's not yet the, okay, so there we go, and it actually petered out this time. Ladies and gentlemen, with diseases with their very long latency periods, it can be hard to see if you've gotten a hold on it. And you can get these kind of waxing and waning, these kind of periods where it grows and then it declines. And it grows and declines. Okay, so we've just seen some statistics there. Now, ladies and gentlemen, I would like to compute a statistic that will involve the number of infections that have yet occurred. How would I do that? There's a couple ways we can do it. I'm going to show you one way. I want to count the number of infections that have occurred so far. How do I do that? How could I do that? Okay. And exposed, right? Yeah, and dead, although they're gone now, so it's kind of hard to count the number of people that have gone in here, gone down there. So we could potentially do that, but here's another way. I'll just show you one way. We could store a count on the numbers that have gotten infected thus far as a variable, for example, in main. This is not the only way. If we didn't have that death, you could actually count up the number in those later states, several such later states. We're going to have count, I'm putting it in main, I'm going to have count cumulative infections. Count cumulative infections, the number of cumulative infections. Is this going to be a double precision value, an integer, a string? It's an integer. It's a count. Okay? Its initial value will be 0. And under what conditions, ladies and gentlemen, will it be changed? What is that? Okay, yeah. When someone is infected, in other words, they transition from susceptible to exposed. So, ladies and gentlemen, we went into main. We created this variable count cumulative infections, and we made an integer variable with initial value 0. And now, in person, what do we need to do? We need to change it, to increment it, right? It's not going to do us any good sitting at 0. So where are we going to increment it? Yeah, at that transition where they get infected, we're going to increment it. So how are we going to increment it? What will I type?
Main.count.
Good. Main.count cumulative infections plus plus. Plus plus just means the equivalent of this equals this plus 1, right? This equals this plus 1. But we can write it much more succinctly, and actually, for those familiar with it, clearly, in the sense that it's very familiar idiom, it's very, very recognizable that you're incrementing this certain thing by 1. That's what we can do. And now, ladies and gentlemen, in the final moments, the closing moments, the twilight moments of this class, we're going to go and create a graph that shows the count cumulative infective, but we'll actually do it on that existing graph, I suppose. So this very top graph that we created, let's go now and add a second component, add another data item. It will be count cumulative infections, and what will its value be? This is in main, remember? It's the top graph I'm modifying. What will its value be? This dot count cumulative infections, right? That's its value, right? Okay. Okay. So let's go run that. So here we go. So now we have our first generation of latents. Okay, here we go. And you could see it accumulating up top. The bottom one, you folks could experiment with it. If you increase the death rate, do you think, how would it impact each of these statistics, do you think? Well, it would limit the degree to which the infection could continue to spread in a grim sort of way. It is self-limiting. It would make it disastrous, but it would keep it from spreading to additional numbers of people. But it would do so in a very adverse sort of way. So there's in terms of how bad an infection there is, we talk about there being transmissibility, how easily it's transmitted, but also how easily how bad it is, how virulent it is within a given individual. And both of those have significant impacts on the number infected over time. Okay, so that's all we have time for today. I've tried to cover a lot of the questions that have come up in the context of our class, and particularly in the form of office hours. I've tried to deliver those, particularly those working on projects or working on problem sets, and going forward. And the existing one, Just Do, is this. Hopefully, this sort of material will be helpful. There's some things we haven't done. If we had more time, I might add recovery from the infection, and I'd have each person accumulate the number of times they've gotten infected before. And that would be an incrementing variable. Keep track of their history of that particular person, which is something that's devilishly hard to do in an aggregate model. It's really not, in general, possible. We can't easily capture that sort of state. We've looked at how we can incorporate statistics, histograms on things, and for those interested in a little bit of interesting fun, I would suggest creating another histogram that shows not the histogram of the number of people to whom a given person is connected, the histogram of the number of people to whom their connections are connected. So go through each person's population, for each of that person's connections, add their number of connections to the histogram, and you'll see something quite different. You'll see something different, and you could puzzle over why. But we don't have time to cover that in class today. I hope this was useful. Next time, we're going to be seeing a new type of modeling, discrete event modeling, for 1 or 2 lectures. And then we'll be talking about common processes, and we'll get glimpses of how we can use all 3 types of modeling in the same model together to give different types of insights. Okay? Thank you. Please put down your. Are these like the sick patients for me to treat? Okay, you can put them down. Yeah. So we're having a model.